So we resume our study of dynamics in the phase plane, and you recall that we were going to analyze the behavior of a two-dimensional dynamical system near a critical point, which we have taken to be the origin, and the set of equations that we are interested in is a linear set of the form Ax plus By and y dot is Cx plus dy, where the constants A, B, C, D are real constants, and we also have assumed that AD minus BC is equal to the determinant of the linear matrix L is not equal to 0. So this is the problem we would like to look at and understand the nature of the critical point at the origin based on the eigenvalues of the matrix L. And we pointed out that the general solution in this neighborhood could be written as linear combinations of the exponentials of the two eigenvalues of the linear matrix L. L itself arose in a nonlinear system as the Jacobian matrix at the origin of the flow itself, of the vector field F itself. But right now we are focusing on the linear system per se as it stands, and we have seen that the general solution, as I said, is a sum of exponentials. Now if you eliminate either x or y from the set of equations, then this implies a second order differential equation for x, which is of the form x double dot minus a plus d x dot plus ad minus bc equal to times x equal to 0, and similarly y double dot minus a plus d y dot plus ad minus bc y equal to 0. X and y of course would differ in general in their initial conditions, as would x dot and y dot, and you would get different combinations of e to the lambda 1 t and e to the lambda 2 t. If lambda 1 should happen to be equal to lambda 2, then the solutions are of the form linear combinations of e to the lambda t and t e to the lambda t, and we have seen that too. And now we are going to analyze the stability or otherwise of this set of equations depending on what the eigenvalues of L look like. Notice immediately that if you have a matrix L whose eigenvalues, matrix L A B C D, whose eigenvalues are lambda 1 and lambda 2, then we find the eigenvalues by writing determinant lambda times I minus L equal to 0, which implies lambda squared minus A plus D lambda plus AD minus BC equal to 0. Do you notice anything interesting about these combinations? This combination and that combination, they are not arbitrary combinations of A, B, C and D, they are very special combinations. This is the trace of the matrix and that is the determinant of the matrix. So this immediately tells you that if I set T equal to trace of L and delta equal to the determinant of L, this implies that the eigenvalues are given by lambda squared minus lambda t plus determinant equal to 0. So the eigenvalues are functions of the trace and the determinant of the matrix. What does that imply? So lambda 1 comma 2 equal to t plus or minus square root of t squared minus 4 delta divided by 2. And recall that the solutions are exponentials in lambda 1 and lambda 2. So what does this tell you? What does it tell you about these? What does it tell you about these eigenvalues? The fact that they are dependent only on the trace and the determinant, and not on the actual all four coefficients, but just these two combinations. That is going to play a role in what we are going to say next. What are these combinations? What is so special about these combinations? What happens if I do a similarity transformation on the matrix? The trace does not change and the determinant does not change, which means that if I transform these variables from x and y to certain linear combinations of x and y by a similarity transformation, by a coordinate transformation, the eigenvalues would not change, and that has a physical implication, as we will see shortly. So right now, yeah, one is the sum of the eigenvalues and the other is the determinant. So it involves, yes, exactly, the other is the product of the eigenvalues, because this quantity here, the coefficient of the linear term is minus the sum of the eigenvalues, and the last coefficient is the product of the eigenvalues, and these two quantities are independent of what sort of linear transformations you make on the matrix, as we will see in a short while. So the behavior of the eigenvalues is going to be determined entirely by the behavior of T and delta. Therefore, and we will take up this lesson in more detail little later, the entire behavior of the dynamical system near the critical point is going to be governed by just the combinations T and delta. And therefore, we could regard these two as parameters and ask what kind of behavior you have in the T delta plane, which we will do in a short while. But first, what are the various possibilities that you have for these eigenvalues in terms of what kind of quantities can they possibly be, and let us classify them. So we now classify, we start the classification. First, the first possibility of course is that lambda 1 and lambda 2 are both positive. That is certainly a possibility. So let us write lambda 1 greater than 0, lambda 2 greater than 0. The solutions, as we have seen, are exponentials in lambda 1 and lambda 2, e to the lambda 1 t and e to the lambda 2 t. So as time goes on, what happens to these exponentials if both are positive? They increase, they are growing exponentials, and therefore the flow would be away from the critical point in all directions, and you would say this is an unstable critical point. Let us look at a simple example and then we come back and formalize this in terms of the actual classification here. So the example that we are going to look at, and each time on this side of the board I am going to give an example. X dot equal to x, y dot equal to y. What is the linear matrix L now in this case? Just the unit matrix, and the two eigenvalues are +1 and +1 each, repeated eigenvalue. What would you say is the solution to this? Let us draw the phase diagram now. Here is x and here is y, here is the critical point, clearly unstable in this case because everything is going to flow outwards. If I started with y equal to 0 at any point on the x axis, I flow outwards. If I start anywhere here, I flow outwards, anywhere here I flow outwards, and anywhere here flows outwards. If I start at any point here, it is clear you are going to flow away in this fashion. So the phase portrait in this case is exceedingly simple, and it just a set of lines flowing out in all directions. What would you say is the stability of this critical point? Unstable, and this kind of critical point is called an unstable node. What would have happened if the two eigenvalues had been unequal in this case? Suppose this had been y dot equal to twice y. What would the flow look like in this case? The two eigenvalues are 1 and 2, they are both positive and the flow is again outwards, but what sort of shape would the flow lines have? It is evident from this that x goes like e to the power t while y goes like e to the power twice t. So therefore y goes like x squared, and what would the flow lines look like in this case? If y, you start off with y equal to 0, you are still going to be like that. If you start off at x equal to 0, you are still going to do this. But if you started off with finite values, positive values say of both x and y, the y is going to increase much more rapidly than the x, like the square of x actually. So it is actually going to flow off in this fashion or in this fashion here or here or here, and therefore the phase portrait looks like this. except for a flow along the y axis itself, the rest of the flows have a common tangent, which is the x axis in this case. This too is an unstable node, it is just a different set of eigenvalues. Of course, if I change this to 3y or any multiple of the exponent in x, the coefficient in x, you are going to have slightly different shapes of this parabola. Had the coefficient of x been larger than the coefficient of y, the whole situation would have been reversed and you would have had parabolas flowing out such that the y axis is the common tangent, but it is still an unstable node. Now what would you say would be the situation if you did not have decoupled equations of this kind? Remember that, notice that in this case the coefficient of y is missing here and the coefficient of x is missing there, so it is already a diagonal matrix. But in general I do not have a diagonal matrix, L has got both x and y on both sides. What would you say would be the flow in that case? Can we deduce what the flow would be in geometrical shape based on the fact that in the decoupled case it looks like this in general? After all, you could regard ax plus by and cx plus dy as linear transformations of the x and y coordinates by the matrix A, B, C, D, which is non-singular. And what does it do? If I take two axes x and y and I go to linear combinations ax plus by and cx plus dy, what sort of coordinate axes do I get in general? It could be rotated, but rotation still leaves the angle between the x and y axes, the two axes, 90 degrees. But in general that does not have to be the case, I could go to oblique axes. Moreover, the scale of x and the scale of y are also changed because these are factors which actually change, they magnify or demagnify. So the most general linear transformation that you can induce, which leaves the origin unchanged, is precisely by a set of linear equations of this kind. If I put u equal to ax plus by and v is cx plus dy, then in general the u and v axes are not at right angles to each other. The scale on one direction could have been demagnified or magnified, and similarly for the other direction. In pictures this means that I could start with a set of axes, and if I have a little square of this kind and ask what happens to this after the transformation, if it were a pure rotation it would just look like this, still a square, it would look like this. If on the other hand it is not a rotation but a magnification in one direction and a contraction in the other direction, it would perhaps look like this. So I have contracted the x direction and expanded the y direction. On top of these two transformations there is one more possibility, and that is to change the perpendicular orthogonal axes into oblique axes, in other words a shear in some direction. So that would look like this, a shear would take it to some shape of this kind. And a general 2 by 2 transformation, a general 2 by 2 matrix would take this little unit patch and in general push it in one direction, squash it in some direction, expand it in another direction, rotate and shear, and therefore the final product would actually be something like this perhaps. So it has been rotated, sheared and magnified or dilated in some direction or demagnified in the other direction. How many parameters are there in this matrix in specifying L? There are 4 real parameters here. We must make sure that in this way of counting or decomposing a matrix, a transformation, a linear transformation into a rotation, a dilation and a shear, we stick to the same number of parameters. And I put it to you that a general 2 by 2 linear transformation of this kind, non-singular matrix, induces a transformation which is a combination of a rotation, a dilation or a magnification and a shear. And the number of parameters needed to specify a rotation is 1, just the rotation about from the reference axis, x axis in the plane. So there is one parameter here, this has 2 parameters for the 2 axes, and that is 1 plus 2 is 3, and this gives the angle of shear, that is 1 more, that is 4, and that is exactly the same number there. You can count this in several ways, and this is not a unique decomposition, but this is one of the ways of decomposing a general 2 by 2 matrix. You can decompose it into a rotation, a dilation and a shear. If we accept that this is all it does, then we can write down what the general flow would look like once you induce those transformations on this decoupled case. And what would it look like? It would simply look like some oblique axis of this kind and perhaps etc. So the moment I see a flow pattern of this kind, I know it is an unstable node, and it is just found from this simple case by a linear transformation of coordinates of this kind. And therefore, we assert that both eigenvalues positive corresponds to an unstable node. Notice there are two different kinds of nodes in pictures. One of them is this generic case where the two roots are unequal, and typically you would have a common tangent to all the trajectories except for a single exceptional direction. On the other hand, the earlier case we looked at had a star pattern and a radial pattern in which you had straight lines emanating in all directions. Do not have to be straight lines, but the fact is that all directions, there are no exceptional directions at all directions the flow moves off and there is no common tangent. Okay. These are two subtle distinctions between, further distinctions between kinds of nodes that one has, but it is not really very relevant here, and right now we are concerned with the fact that two positive eigenvalues implies an unstable node of the, we will come back to this, we will explain what sort of flows would have this extra, this common tangent, etc., in specific instances, in examples. Okay. What would happen if both the eigenvalues were negative? Less than 0, lambda 2 less than 0. All the arrows would be reversed because you would have damped exponentials, and this means that as t tends to infinity, wherever you start you are going to flow into the critical point at the origin asymptotically, and therefore I would call this an asymptotically stable node. The reason is I would like to be careful about the definition of stability, so let us for the moment call it an asymptotically . We will distinguish shortly between stability and asymptotic stability, and they are different concepts altogether. This is asymptotic stability. We are guaranteed that once a trajectory enters the neighborhood of this point, the critical point, then as t tends to infinity it inevitably falls into this critical point, that is asymptotic stability. The third possibility is if one of the eigenvalues is positive and the other eigenvalue is negative. Once again, all we have to do to study this is to look at a decoupled case, a case where the matrix is already diagonal, and then argue that a linear transformation of that picture would give us the true picture near a situation which corresponds to one positive eigenvalue and one negative eigenvalue. So all we have to do is perhaps to do the following, right, x dot equal to minus x and y dot equal to plus 2y. In this instance x goes like e to the minus t, flows into the fixed point where the critical point, whereas y flows into 0, whereas y explodes outwards like e to the 2t. So we know the solutions. What does the flow look like? Well, on the x axis, since it flows in, you have this picture, and on the y axis, since it flows out, you have that picture. If you start with some point here, some value of x which is not 0, say some negative value, then it has got to flow in towards 0, but the y has to flow outward, and therefore the trajectories look like that, and by continuity this is what they would look like. Would you call this a stable or an unstable critical point? I'd call it unstable. I'd call it unstable because except for very special initial conditions, in other words y starts at 0 and remains at 0, if you are on the x axis to start with you flow in, but wherever else you are on the plane you are actually going to go away to infinity in some direction or the other, therefore this is unstable. What is the shape of these trajectories? It looks like hyperbolas, but actually they are not hyperbolas unless of course the coefficients are equal in magnitude. Then of course you would have something like xy equal to constant and there would be rectangular hyperbolas. If you had x dot is minus x and y dot is minus y, then of course xy is constant and then they would look like rectangular hyperbolas. But right now that is not happening. The y variable is exploding much faster than the x variable is going to 0, but they look hyperbolic in shape, roughly in shape. This is an unstable critical point and it is called a saddle point. So that was this is a saddle point. Again, if I had a situation where I have a general L with two real eigenvalues, one of which is positive and the other is negative, the flow would look like a distortion of this picture by the same sort of coordinate transformation we looked at earlier, and therefore in general perhaps this is what a saddle point flow would look like. There would be two directions in which the flow goes in, another one in which it goes out, and the rest of the trajectories would follow curves of this kind. And the whole plane in this case would be striated by these curves. This fashion. And that point itself is a trajectory by itself and it is unstable. Although I draw all these pictures with these lines going right through that point, remember that that point is a trajectory by itself, but you can come arbitrarily close to it, and that is the reason I draw these as continuous lines. It is natural to call this the unstable direction and this the stable direction associated with this saddle point. We will say much more about this as we go along. So that is what a general flow near a saddle point looks like. In this linear case, these lines are actually straight lines, as you can see, but in a general case with the nonlinearity present, the first thing that would happen is that these things, although arbitrarily close, very close to the critical point, they would tend to be straight lines. The actual flow lines would be curved in general, so you won't have straight asymptotes as you have here in a nonlinear system. That too will play a role. So we have the third possibility, namely it's a saddle point here. Remember, we have ignored the case where one of the eigenvalues can be 0, one or both eigenvalues can be 0, because I said we are going to look at all those cases where the matrix is non-singular and therefore it can't have 0 as an eigenvalue. We have to look at it separately. We have to ask what happens when the eigenvalue, one or more of the eigenvalues is 0. What other possibilities exist? Have we exhausted everything? Complex eigenvalues, absolutely right. We have complex eigenvalues possible, and the first thing that would happen is first thing we have to recognize is that since these coefficients are real, the complex eigenvalues would be a complex conjugate pair. Therefore, all we have to look at is a situation in which 4 lambda 1 comma 2 is some lambda plus or minus I mu, where lambda and mu are real numbers and lambda is greater than 0. The behavior of these trajectories is not really crucially dependent on whether mu is positive or negative. It is irrelevant because e to the I mu t is going to be just cosines and sines of mu t. On the other hand, you have an e to the lambda t, and if lambda is positive it is going to flow outwards, if lambda is negative it is going to flow inwards, but there is going to be an oscillation in the sign of x and y because of e to the I mu t present there, because that is going to lead to cosines and sines which would change sign as t increases. What then would the flow look like? Again I go to the phase plane, here is x and here is y. If the flow has a positive value of mu, it means as time goes on x and y would change sign but would flow away from the origin, and they would oscillate with an increasing amplitude and go off. So what sort of curve would you expect? You would expect a spiral, quite right, but it would be an outward tending spiral, it would go off in this fashion. You know that because e to the power, so let me write it here, e to the lambda 1 t for example would be e to the lambda t e to the I mu t, which would be e to the lambda t times the cosine of mu t plus I sine mu t. And of course superpositions of e to the lambda 1 t and e to the lambda 2 t would involve these cosines and sines, and the coefficients would be adjusted so that the linear combination is real because we are looking at real variables. But the fact is, because of the cosines and sines, although this increases as a function of time monotonically, these functions would change sign, they would oscillate between positive and negative values, and all the while the amplitude would increase. So in a picture like this, if I start at some value here of x, a little later the value is larger in magnitude but opposite in sign, and then once it comes back here it is again larger in magnitude but opposite in sign, and the same thing is true for y. So it is intuitively clear that the picture is actually that of an outward spiral, outward moving spiral, and this case therefore is called an unstable spiral point. There are other names for this spiral point, one of which is the word focus. Occasionally called a vertex as well, but focus is much more common. But I would like to stick to the word spiral point, the phrase spiral point, because this is evocative, it tells you exactly what the trajectories look like. Once again, if I have a linear transformation on this spiral, what sort of distortion would this spiral undergo? What would it look like? And that is not hard to see. It could get squashed in one direction, turned around and extended in the other direction maybe, therefore it would perhaps look in this fashion. This would be the general flow around a spiral point which is unstable. And it is unstable because lambda is positive. And exactly as in the case of the nodes, we could assert that if lambda 1, 2 were of the form lambda plus or minus I mu with lambda less than 0, the arrows would be reversed and the system would flow into the critical point as t tends to infinity, and this would lead to an asymptotically stable spiral point. The arrows would just be reversed. Whether the spiral is wound inwards clockwise or counterclockwise depends on the details of the problem. It would actually depend on the direction in which the phase trajectories are traversed. That would depend once again on the coefficients a, b, c, d, etc. But this is what happens when you have a complex conjugate pair of points. There is one more possibility, and what is that? There are subclasses here between, in these cases when I have for instance two equal roots, both of which are positive, both of which are negative, or one of them is positive and the other is negative and they are equal in magnitude. Those are subclasses of what we have looked at, but what would happen, there is one more class which is distinct. Lambda is, both the eigenvalues are pure imaginary, they form a pure imaginary complex conjugate pair. So lambda could be 0 and yet determinant L is not 0 because the eigenvalues are plus or minus I mu. Then that is the final case. Let's write that down. 6 lambda 1 comma 2 equal to plus or minus I mu, where mu is a real number. The simplest example of this is in fact the simple harmonic oscillator. We have studied that over and over again, but let us write that down. And that, if you recall, corresponds to a problem in which x dot is p over m, where p is the momentum of the oscillator, and p dot, which is the rate of change of momentum, is equal to the force on the oscillator, which is minus m omega squared x, or minus kx, where k is the spring constant. What does the matrix look like? This is a linear system in which L is equal to a 0 here, a 1 over m here, a minus m omega squared here, and a 0 here. This implies lambda 1 comma 2 equal to, what are the two eigenvalues in this case? Plus or minus I omega, and as all of us know, the solutions are linear combinations of e to the I omega t and e to the minus I omega t. What do the phase trajectories look like in this case? Instead of y I have p here. They do not necessarily have to be circles. The scales on the two axes may be different, and they are generalizations of circles, so they are really ellipses of some kind. And so on. The entire plane is striated by these, laminated by these ellipses, concentric ellipses. Would you call this critical point here, would you call this stable or unstable or asymptotically stable? What would you call it? I certainly won't call it unstable, because the trajectories do not disappear from its neighborhood, they do not blow away from it. On the other hand, they do not fall into it either, they just go round and round. So we call this a stable critical point, and this particular case is called a center, so it is a stable center. Notice that I have said stable and not asymptotically stable. So the time has come now to distinguish between stability and asymptotic stability, and these are two different concepts altogether. One does not imply the other, as we will see in a second. I define a critical point to be stable if the following is true, and this is doable rigorously, but let me give an operational definition which is easy to understand. So stable. Here is the critical point, and here is some neighborhood of this critical point. Then a stable critical point is one where a trajectory, if it has once entered this neighborhood, never leaves this neighborhood. So something which has entered it may do all kinds of things inside here, it may fall into it, it may also keep going around, or it may do this. But it never leaves this neighborhood, and I call that a stable critical point. If this neighborhood is U, once a phase trajectory enters the neighborhood U, it never leaves it. It does not have to be asymptotically stable. This one, you would say, if this is the situation, I would say that this critical point these trajectories tend to this point, and therefore we are going to have asymptotic stability, but stability does not require that. It suffices that a trajectory which once it enters this neighbourhood remains in this neighbourhood forever, and that is exactly what happens here. If this is a neighbourhood, there exists a trajectory, there exist trajectories which remain in this neighbourhood forever.
So the concept of stability depends on the neighbourhood.
The concept of stability depends on the neighbourhood. So like everything else, you are going to have to perturb the system a little bit away from the critical point and ask what the trajectories do always. That is how stability is defined in any case. It is not a concept applicable to a single point, but to a region.
So like if I call a particular point a stable point or whatever,
yes,
I need to tell what under what neighbourhood it is stable.
You need to know if there are other critical points in there. So the question you are asking really is, how big can this neighbourhood be? In this case there is just one critical point. So the entire plane, there is a single critical point, and no matter what neighbourhood you give me, there exist trajectories which, having once entered the neighbourhood, never leave this neighbourhood altogether. If I have more than one critical point, then the question that you raise comes up, and we will see what happens when you have multiple critical points. But right now just think in very elementary terms. If I look at mechanical examples, I would say that a stable equilibrium in a potential problem is if the potential has a minimum, but the idea of a minimum is not a concept restricted to one point. It says something about not only the function at that point and its slope, but also about its curvature at that point. So it is really a non-local concept in that sense. It talks about a neighbourhood of this point, and that is always going to be the case. So I say that a critical point is a stable one if there exists a neighbourhood of this critical point such that once a trajectory enters this neighbourhood, it never leaves it as t tends to infinity. What then is asymptotic stability? Well, asymptotically stable again, a critical point, this point is asymptotically stable if a trajectory which starts in this neighbourhood tends to this point as t tends to infinity. You are guaranteed that every trajectory that starts in this neighbourhood tends to that point as t tends to infinity. So every point, every trajectory starting in U tends to the Cp as t tends to infinity. So if something starts here, it is guaranteed to fall into this asymptotically as t tends to infinity. Does asymptotic stability imply stability? It is clear that stability does not imply asymptotic stability, because it could keep going around, it does not have to fall in. But does asymptotic stability imply stability? Not necessarily, because you could start here, you could in fact do a thing like this. So it could be a spiral, it goes out very far away, but it is guaranteed to come back. So it starts off, does this, goes around, and eventually falls into this point here. So it certainly does not have to be stable. Therefore stability and asymptotic stability, they are not concepts, they are independent concepts altogether. You could have a trajectory that is stable as well as asymptotically stable. You could have a critical point which has that property, but it is not necessary. Centers particularly are stable, not asymptotically stable, and spiral points, stable, asymptotically stable spiral points could have behavior like this. They need not be stable, but they would definitely be asymptotically stable. Yeah. The statement is that there, given a neighbourhood, there exists this sort of behavior. We can make this much more rigorous, but I am just trying to do this in heuristic terms right now till we have a few examples under our belt, and then of course we could look at more tests for stability and so on. So one of the things we are going to do is to have a kind of nonlinear test for stability which does not depend on linearization as we have done here, and that is Lyapunov's direct method, and we will talk about it a little later. Yeah. Did anyone have a question? Okay. So a center in particular is stable but not asymptotically stable. This is an important point and we will see why in a short while. This exhausts all possibilities of those cases where the determinant is not 0. And now can we make some sense out of this? I already mentioned that everything seems to depend on T versus delta, T and delta, just these two combinations which are unchanged under similarity transformations on the matrix, and therefore it is clear that the nature of the critical point is kind of independent of these transformations. It does not depend on the particular choice of coordinates x and y. Linear combinations of this x and y would still leave the nature of the critical point unchanged, and that is very important to know because this is a very robust property that we are talking about. Okay. Now what can we say about this classification in general terms? We can draw a little picture in parameter space. So I draw T on this axis and the determinant delta on this axis. It is obvious from here that the case delta equal to 0 is on this line, and that is the case I am going to ignore at the moment, and the curve T squared equal to 4 delta would separate regions where the eigenvalues are complex from those where the eigenvalues are real. And what is the curve T squared equal to 4 delta? It is a parabola. So on this curve T squared is 4 delta, and outside T squared is greater than 4 delta, whereas inside T squared is less than 4 delta, and then the roots are complex. What sort of behavior do you have here where delta is negative? If delta is negative, the square root of this number is certainly bigger than T in magnitude, and therefore one eigenvalue is positive and the other eigenvalue is negative. Therefore below this axis you have entirely saddle points, one positive eigenvalue, another negative eigenvalue. So this whole place is saddle points, and the flow looks like this. Whether you are on this side of the graph or on this side does not matter, you just have saddle points and the whole thing is unstable. Everywhere in parameter space in this region you are guaranteed to have unstable saddle points. What happens when you move up here? If you are here, say T squared is greater than 4 delta certainly, but what happens now to these eigenvalues? Both are positive? It is an unstable, this place is unstable, but what sort of unstable point do you have? What sort of unstable point do you have? Two positive eigenvalues, unstable nodes, so you have unstable nodes, and therefore the picture would be perhaps something like this. What would you have here? You would have stable nodes, asymptotically stable nodes. So asymptotically stable nodes. In this region, and these are unstable nodes in that region. What would you have here when T squared is less than 4 delta? T is positive, remember you are on the right hand side, so T is positive and this becomes pure imaginary, so the square root gives you plus or minus I times something or the other, but then you have a positive real part and therefore you have unstable spiral points. So unstable spiral points. flowing away. And what would you have here? You would have stable, asymptotically stable spiral points. So in this case the flow is inwards. What do you have on the vertical axis? T is 0. You have centers. So on this case, in this case right here you have centers. All along this point you have centers. So essentially you have this sort of behavior. We now come to a very important concept. This picture is sufficient to tell us why this is so, why this happens to be so. If I start somewhere here and I perturb these parameters a little bit, I change A, B, C, D a little bit, I may wander to this place, but what was an unstable node remains an unstable node. Similarly, if I move around a little bit here, nothing much happens. If I move across this line, I go from an unstable node to an unstable saddle point. If I move across this line, of course, is a big change. I go from something that is asymptotically stable to something that is unstable, but then we have crossed the line of degenerate or higher order critical points where L becomes singular. But with that exception, everywhere else, if I cross this line, what was an unstable node becomes an unstable spiral point. What was an asymptotically stable node becomes an asymptotically stable spiral point. But if I am on this line and I perturb parameters a little bit, if I move to this side it becomes unstable, if I move to this side it becomes asymptotically stable. So you can see that this line of points, the line of centers, is structurally unstable in the sense that a small change of parameters can completely change the qualitative behavior of the critical point. So we have our first statement which is somewhat general, which is centers are structurally unstable. When mathematicians say structurally unstable, they mean that if you change parameters slightly, then there is a qualitative change in the behavior of the system, and this is exactly what happens to centers. What sort of physical motion does that example of a center correspond to? You have pure imaginary eigenvalues. So what's special about this motion? Periodic motion, periodic motion. So this implies that periodic motion is structurally unstable. Small changes can get you completely away from periodic motion. I add a little bit of friction here, I add a tiny bit of friction here, and this becomes, this thing has another term m gamma x dot, where gamma is a friction constant, assuming the friction to be proportional to the instantaneous velocity with the retarding coefficient gamma, and I use an m gamma there so that gamma has dimensions of time inverse. Then you immediately see that this thing here has minus m gamma here in this point, oh sorry, m gamma times x dot, so let us call this minus gamma p, minus gamma here, and then of course the eigenvalues are not equal to plus or minus I omega. What happens to the eigenvalues? What are the eigenvalues of this? They are minus gamma, they are gamma minus gamma plus or minus I omega, right, and therefore the eigenvalues do not look like this at all. What sort of critical point is the origin now? Asymptotically stable spiral, provided gamma is positive, provided the friction acts as a retarding force. If the friction does not act as a retarding force but pushes you along in the same direction even further, if there is positive feedback, then of course it becomes unstable. So this means that the phase trajectories in this case would reduce to something like this. This is the case of ordinary friction, gamma greater than 0. So introducing a small gamma pushes you from here to this region to asymptotically stable spirals. If gamma had the wrong sign, then of course you would become unstable and it would move into the other direction altogether. So that is why periodic motion is so fragile, it is not robust at all. Conditions have to be just so in order to have periodic motion, and they are really the exception rather than the rule. This has further implications in dynamical systems. For example, although I will say it in loose terms now, we will look at it more rigorously later. Heartbeats, if they are too regular, that is not very good. So if you look at the heartbeats of young infants with very robust hearts, they are actually extremely irregular in some sense. They are on something like a chaotic attractor, which is very robust, structurally stable. Small perturbations do not push you off this attractor. On the other hand, if the heartbeat gets extremely regular and becomes periodic, you have to worry, because this implies that a small change could cause you to have an explosive growth on either direction, which is not very good. So again, this is a lesson of some generality. Centers are structurally unstable. This is important to remember here. Now once we have this classification under our belt, we really can generalize this and go on in very many directions. And the first question I want to ask, which we will dispose of right away, is that the eigenvalues depended on the trace and the determinant in this case. If you go to higher dimensions instead of 2 by 2 systems, xy systems, if I look at higher dimensional dynamical systems, n dimensional systems, then the linearized matrix would be n by n. It would then have n eigenvalues, and once again we expect that the eigenvalues are independent of similarity transformations. They are stable against similarity, they are invariant under similarity transformations, which would imply that the eigenvalues should be writable in terms of quantities which are invariant under similarity transformations of the matrix. In the 2 by 2 case, we know that the trace does not change and the determinant does not change. What happens in the 3 by 3 case? You need 3 such combinations. Where are you going to get them from? Once again, the trace of this matrix does not change and the determinant does not change, but you need one more. Where is this going to come from? And in the n by n case, we need to have n invariant combinations. Where are these going to come from? I need n of these quantities. The determinant is just one of them. I am willing to put that down, but that does not give you n of them. For the 2 by 2 case, that was sufficient. Where are the others going to come from? Well, we do know that the coefficients in the secular equation would be the product, the sum of all the eigenvalues, the products 2 at a time, 3 at a time, and so on and so forth. So what invariant quantities are they functions of? You need to put everything in terms of quantities which do not change under similarity transformations. No, not quite. I mean, in terms of L, what are the quantities that would be unchanged? What happens if I square the matrix L and then take the trace? What would that be? For the 2 by 2 case, what is the square, what is the trace of L squared? Well, imagine you have diagonalized L, you can't always diagonalize a matrix, but imagine you have diagonalized it. What does the L squared look like in the diagonal form? Exactly, lambda 1 squared plus lambda 2 squared, and what is the trace of that? What is the trace of a diagonal matrix with elements lambda 1 squared and lambda 2 squared? Just the sum of these two. So it is quite clear that if you give me lambda 1 plus lambda 2 and lambda 1 squared plus lambda 2 squared, I could certainly find lambda 1 and lambda 2, because I would straight away find lambda 1 lambda 2 by combining these two, and then I could find lambda 1 and lambda 2 independently. So what would be the generalization of that? Absolutely, it would be trace of L squared, trace of L cubed up to the trace of L to the power n. It is easy to check that AD minus BC in the 2 by 2 case can really be written as a combination of the trace of L squared and the trace of L the whole squared. So these are the invariant combinations. You are guaranteed that these combinations do not change under similarity transformations, and that is what the eigenvalues are functions of. After all, the statement is that if you give me lambda 1 plus lambda 2 up to lambda n, lambda 1 squared plus lambda 2 squared up to lambda n squared, and similarly lambda 1 to the power n summed till lambda n to the power n, then I can find all the lambdas in terms of these quantities, they are invariant. So this generalizes what we know for the 2 by 2 case. Just a side remark, when can you diagonalize a matrix? We can always find its eigenvalues by writing determinant lambda I minus L equal to 0, and that is an algebraic equation of the nth degree, and it has n roots in the complex plane. What would be the case and what would be the condition for diagonalizing a matrix by a similarity transformation? When can I take a matrix M and find a similarity transformation S such that this is a diagonal matrix? And of course once it is diagonal, its elements are just the eigenvalues of the matrix. Under what conditions can you diagonalize a matrix by a similarity transformation? This is not always possible. You can always find the eigenvalues, that is a different problem from diagonalizing the matrix. There are lots and lots of matrices which are not diagonalizable by similarity transformations. A sufficient condition for you to diagonalize a matrix, a sufficient condition is that the matrix M commute with its conjugate, Hermitian conjugate. If this is true, by this dagger I mean the Hermitian conjugate of this matrix, which is the transpose complex conjugated. That is a sufficient condition for M to be diagonalizable by a similarity transformation. Such a matrix is called a normal matrix. Okay, so we stop at this stage and take it up from here.